Hello, today we're going to start to learn about Earth systems and how we can break down and understand Earth's 4.5 billion year history. So, first, you need to know what a system is. In this class, in Earth space science, a system is a collection of processes that are all interacting. Physical, chemical, biological things that involve matter and energy flowing that makes up a system. It is a collection of stuff interacting. Earth is made up of 5 systems, and as we're going to see, all of these systems also interact with each other. So, really, Earth is one big system that is made up of 5 smaller systems. Those 5 systems are the atmosphere, all of the air that surrounds Earth, the hydrosphere, all of the surface water, lakes, rivers, and oceans, the geosphere, which is the solid earth, the crust, the ground that we walk on, the cryosphere, which is frozen water, glaciers, frozen parts of oceans, etc., and the biosphere, which is all of the living organisms. The atmosphere, hydrosphere, geosphere are the 3 that we're going to talk most about right now. The cryosphere we'll talk about in a couple of weeks. So we know that Earth formed in a protoplanetary disk about 4.6 billion years ago. But when it formed, it was a molten ball of rocks, and a lot has changed since then. So first, let's look at the atmosphere. We've gone through kind of 3 main atmospheres. When Earth first formed, the atmosphere was mostly made of hydrogen, helium, ammonia, and methane. Methane is a very good greenhouse gas, so this atmosphere kept Earth hot. It kept the rocks molten. It was a hot, violent place at the beginning of Earth's history. Hydrogen and helium are both very light elements, though. So this atmosphere quickly was blown away. It got burned off, and this atmosphere did not last for very long. The second atmosphere came from the impacts of comets and asteroids and from a process called outgassing. Outgassing is like rocks farting. When a molten rock cools down and hardens, all of the gas is trying to escape before the rock hardens. And so outgassing is the process of gas being released. If you have ever been interested in pottery or ceramics, then you know you need to get as much air out of your clay pot or whatever it is before you put it in the kiln, before you fire and harden your pottery, because otherwise the gas would try to escape and end up breaking your creation. Here, gas is heated and is trying to escape before the rock can cool and harden. And if it doesn't make it out, it's going to break the rock trying to get out anyway. Outgassing still continues today, mostly now as volcanic emissions. Coming from volcanoes as volcanic rock hardens. And mostly it is water vapor, carbon dioxide, and nitrogen that is being released by these rocks. There are trace amounts of other gases as well. The third atmosphere that we care about came when oxygen entered the atmosphere and became important, but that didn't happen until plant life formed, until there was photosynthesis. And then the plants were decreasing the amount of carbon dioxide and increasing the amount of oxygen. As oxygen became more abundant, the ozone layer was able to form, which gives us a lot of protection from the sun and really is what allowed life to flourish. We are going to talk much more about the different layers of the atmosphere and what the ozone layer does for us when we learn about the atmosphere in March. So here's a graphic that shows the atmosphere over time. You can see the hydrogen and helium did not last for very long. They burned out very quickly. And the ammonia and methane slowly left as well. There was a lot of water vapor in the beginning, and you'll see that cut off quickly. This water vapor all came from comets, asteroids, and outgassing. Almost all of the water on Earth was carried to Earth by comets and asteroids. In the violent beginning of the solar system, we were constantly being hit by different space rocks, and a lot of them carried water with them that were brought to Earth. Then we had not until much later in Earth's history, a billion or 2 billion years ago, we start to see photosynthesis and plant life really giving us oxygen and allowing here a ozone layer to form. And oxygen has stayed pretty steady since then. Nitrogen has just kind of always been the background gas. It has been there since the beginning, and as other gases fluctuated, went up and down, nitrogen has just kind of always been there. And so it brings us to our current atmosphere, which is mostly nitrogen and about a quarter oxygen, plus some other small gases. The hydrosphere, all of the liquid water on Earth, mostly was brought here by those water carrying comets and asteroids. And once it cooled enough, once this incredibly hot atmosphere burned off and wasn't around much anymore, you see all of this water vapor fairly quickly leaves the atmosphere. It rained for years. It just rained and rained and rained until we had the oceans. So the water all falls to earth and fills the oceans. The molten rock underneath is able to start to harden and form ground, but here's underwater. And all of this water falling and becoming the oceans diluted the carbon dioxide in the atmosphere, which really helped allow nitrogen to become abundant. As carbon dioxide disappears, nitrogen is filling that gap. The geosphere, finally, is the crust that forms as magma cools and hardens. This led to the creation of tectonic plates. We're going to learn about tectonic plates right at the start of the second semester. But it is the collision and diversion and sliding and grinding and movement of tectonic plates that created the continents. And we're going to see exactly how that happened when we learn about that in January. So we've got 4.5 billion years. We got to break that down into chunks of time that are easier to understand. 4.5 billion years is hard to wrap your head around. So geologists will use what they call the geologic timescale to break that down into easier chunks, looking at it one piece at a time. This is what the geologic timescale looks like. And I know that at first glance, this is an incredibly overwhelming image. Look at it as 4 different columns, and it kind of cycles through. So Archean is the oldest, moving up and getting younger. Maybe you notice Triassic, Jurassic, and remember that that's dinosaurs going up, and the Neogene, all of this is the most recent time. So we are all the way up here. The formation of Earth is all the way down at the bottom. And you might notice that there are different divisions here. We break down all of that long history of Earth into different chunks in order to help understand it. The same way you can break a year down into months and weeks and days, we do the same thing with geologic history. The important thing to remember here is that these divisions aren't necessarily even. It's not like 50 million years makes an era or anything like that. That is not the case. These divisions are decided typically based on big events, new dominant form of life, a catastrophic event like a mass extinction. These are the kinds of things that define the end of one time period and the beginning of the next. So the largest division of time is an eon. There have been 4 eons in Earth's history. Again, not evenly divided. They are between 500 million and 2 billion years long each, but the eon is the largest division. We break eons down into eras. An era is a more general time span. The Phanerozoic eon, which is the current eon, has been divided into 3 eras: Paleozoic, Mesozoic, and Cenozoic. We are living in the Cenozoic era within the Phanerozoic eon. So you can think of an eon is a year, an era is a month within that year. Then if we break it down even further, we can break eras into periods. So the Mesozoic era is divided into 3 periods: the Triassic, Jurassic, and Cretaceous. So this is just breaking it down even further. If an era is a month, then a period is a week. It is a smaller chunk of time to focus on. Lastly, sometimes we will divide periods into epochs. Some people will say epoch. Both are correct, epoch or epoch. And these are mostly used to break up the most recent periods. Like I said, it is when there is a new dominant form of life or a mass extinction or some big event that defines the end of a period and the start of the next period. With most recent history, we have a lot more fossils and a lot more evidence. So it becomes easier to break it down into smaller chunks. You can draw clearer lines and see all of these very specific chunks. So if an eon is a year, an era is a month, a period is a day, and an epoch or an epoch, a period is a week, and an epoch or an epoch is a day. So that is how we divide time. We're going to spend some time in the next couple of classes learning much more about these different eons and eras and periods and understanding exactly what was going on Earth during those times. So to see it again, this one goes the other way. The Hadean is the oldest eon. It covered about 500 million years. Then we went into the Archean eon, which covered 1.5 billion years. Then there was the Proterozoic eon, which covered about 2 billion years. And lastly, we are in the Phanerozoic eon right now and have been for about 500 million years. The Phanerozoic eon is broken into these 3 eras. The Paleozoic era came first, the Mesozoic era came second, and the Cenozoic era is the current era. And then you can see we have broken the eras down into different periods that span various amounts of time. If we were to go even further, we would break the periods up into epochs. But like I said, that happens really only with the most recent history because that's what we know most about. That's the easiest to study. So that is your introduction to Earth systems and history. In the next couple of classes, we'll be talking much more about what exactly was going on in each of these time periods. Bye-bye.